Hello, this video is about Hooke's law and elastic potential energy in materials. But let's start off by looking at some various materials because materials are very important in engineering and in everyday life indeed. So here are a few images to sort of get us set in the context. This first one is a picture of the Millau Bridge in France. This bridge was a design challenge and an engineering miracle effectively. Very, very important piece of engineering made mainly from steel and concrete. Over here we've got the Arcelormittal Tower, or the Orbit Tower from the 2012 Olympics. Again made of classical materials such as steel, but precision engineered. Here we've got a Formula One race car made of more exotic materials such as carbon fibre. Every single detail of this car is looked at in terms of its material structure. And here we see possibly a glimpse of the future with a smartphone, a concept smartphone by Samsung with a curved screen, which are now appearing on the market. And underneath there we have a little microscope image of a sheet of very, very thin material that engineers and scientists are starting to use in modern life. So that's kind of a context, but all materials have various properties, and we're going to look at a couple of those. So let's start from real basic stuff. The only thing we're going to deal with at AS is one-dimensional forces acting on solid materials. So those forces can either push into an object in this way here, which will put the object under compression. So that's one of our key words here, compression, which is this situation here where the object is being squashed by forces, and this situation here where the object is being pulled by forces in one dimension. And this is an example of putting an object under tension. Now we've seen tension already when we've been looking at mechanics, when we're looking at statics and equilibrium problems. We're going to talk about tension causing extensions and things like that now. Okay. So to investigate tension in a material, this is a typical experiment that you either have done or will do quite shortly. This is where you load up a spring. It's typically a spring in a school physics lab with weights, and you measure the extension of the spring. Now the extension is the length of the spring, which is this length here, okay, which we can call L, minus what we call the natural length. Okay, and the natural length is the unstretched length, which we can possibly call L naught, which is our natural length of the spring. And the extension, which is usually given the symbol X, is going to be the length of the spring under load minus the natural length of the spring, L naught. All right, so that's what we're talking about when we say the extension. Now, there are two forces acting here, and it's important to realize which force we're talking about. If you have a spring, and I'll just redraw a little cartoony sketch of it down here, with a weight on the bottom, there are two forces acting. So let's try and identify those forces. The first force is the weight from the masses that you've put on the end of the spring. And the second force is an upward force, which I'm going to call F, which is the restoring force in the spring. The restoring force is the force caused by the spring that's trying to pull it back to its natural length. And so you've got this corresponding pair of forces. Now, if the spring is in equilibrium, i.e. it's still, stationary, then those forces must be equal and opposite. Okay, so they are the same, but it's important to realize that when we go forward through this topic, it's this force, the restoring force in the spring, that we're talking about when we say the force. Okay, so that's that. Right, okay, a little bit of terminology that you need to know. So this first one we've said already, when you load up a material with a force, it results in an extension. Right, the material, typically a spring or a piece of wire, extends, it gets longer. Now, when you remove the load, two things can happen, and that depends on the size of the load as well as the actual piece of material. If the load is smaller and you remove it, the material, the spring, I mean, it's quite handy to think of a spring, so let's stick with spring. So the spring will return to its natural length, i.e. when this weight is removed, the spring will jump back up to this point here and return to its natural length. There will be no actual change in the spring from before to after the loading and unloading. Okay, now when that happens and the spring returns to its natural length, this is the definition of elastic deformation. The spring is deformed, but we say it's deformed elastically. And the definition of that is when the load is removed, the material returns to its natural length. Okay, now that happens for smaller loads. If you increase the load, you increase the force that you're putting the spring under, that will have a different change once you remove the load. So for large loads, when you remove that load, that will result in a permanent change in length. Okay, the spring will be permanently stretched, and I'm sure you can imagine what would happen if you pull this and pull this and pull this by putting more and more and more load on it, put more and more tension in it, and extended it beyond a limit, which we'll talk about in a minute. When you then remove that load, it wouldn't return to this natural length. It would remain permanently stretched. The word we use for that is plastic deformation. Okay, plastic. So you've got two types of deformation: elastic deformation and plastic deformation. Elastic, when it returns to its natural length after removal of a load, and plastic deformation, where it results in a permanent change in length on the removal of the load. Okay, so those are two terms that you need to be able to define. When you plot a graph of extension against force, this is the shape of the graph that results. Now here we're talking about the force in the spring, as we said before, which is why the extension is the independent variable. You stretch it and that results in a force, a restoring force in the spring. So this is not the weight of the weight of the masses that you put on the end, it's the restoring force in the spring. And when you plot these two together, you get a graph that is this shape. So you can see at first there's a linear relationship. All right, so when you extend it a certain amount, the force will be proportional to that extension. But then the pattern changes at this point here. And beyond that, there is a non-linear pattern, usually a curve like this. This is what we call the elastic section of the graph, and this is the plastic section. All right, so in this region here, the spring is undergoing elastic deformation, elastic behavior, and beyond this point, it's undergoing what we call plastic deformation or plastic behavior. This is a limit, and it's effectively the elastic limit because it's the limit of the elastic section, so that's quite easy to remember, the elastic limit. Now there's a little bit more to it than that, but effectively we'll leave it just as the elastic limit. It's not quite the end of the straight line section, but it's close enough to make no difference in our case. Okay, so that's called the elastic limit, which comes pretty much at the end of the straight line section of the graph. Okay, so those are the two types of deformation that you need to know about, and we'll do that, if we haven't already, we'll do that experimentally. So, the first person to do this was Robert Hooke in the 17th century, and he formulated a law that is to do with the extension of the spring or any material under load. And in words, Hooke's law says this: provided the elastic limit is not reached, so we're talking about the straight line section of the graph, the extension of the body is proportional to the applied load. So effectively, as long as we don't go beyond this point here, we have a straight line and a proportional relationship between the extension and the force in the spring, which is equal to the applied load. Okay, so that's this section of the graph, and that's called Hooke's law, that one in the box there. Okay, mathematically speaking, we can express it like this. Because they're proportional, in order to turn a proportionality into an equation, we add a constant, and it's this constant here, which is this k here. Okay, so F is the force, x is the extension, and k is the constant, which we call the force constant, all right? Or for the case of a spring, we call it the spring constant. Now the force constant has units newtons per meter because of the units in this equation, and that's Hooke's law expressed mathematically. There's a little negative sign in here. That's to do with the vector nature of force and extension. Because they're in the opposite direction, we have a negative sign in there. Now usually we ignore that because we're only interested in magnitudes. Okay, so that's Hooke's law expressed mathematically. force is proportional to extension, and the constant of proportionality is K, which gives us F equals Kx. So here's an example of that. We have a wire and we put a load of 20 newtons on it, which causes an extension elastically, all right, of 0.004 meters or 4 millimeters. So because it's elastic extension, we can use Hooke's law to calculate the force constant of the wire. So rearranging our equation, we've got K equals F over X, X being the extension, which is going to give us 20 divided by 0.04, which is a force constant of 5,000 newtons per meter, which means if you could stretch it by a whole meter elastically, you would need a force of 5,000 newtons. That's quite a high force constant. Springs tend to have a slightly lower force constant, anywhere between sort of 10 and 100. But for a wire, it takes a lot more force to extend it. So that's why wires tend to have higher force constants than springs. Okay, so that's Hooke's law. So let's move on a little bit. Obviously, it takes work to extend a spring, and the work done on the spring results in a change in elastic potential energy in the spring. Now, the elastic potential energy, the energy stored in the spring, effectively, is equal to the area underneath the force extension graph. All right, so if you take any value of the extension, for that value of extension, the energy stored in the spring will be this area, the area of this triangle, underneath the graph. Now obviously beyond the elastic limit it's difficult to calculate the area because we don't have a straight line, but inside the elastic limit, before the elastic limit is reached, which is obviously about there, then that can be quite easily calculated from the area of the right angled triangle. So here's a little derivation. So work is equal to change in energy, and in this case the change in elastic potential energy. And because we've got force against extension here, right, the area is going to be half the force times the extension. That's half the base times the height of this little rectangle here, okay, because it's right angled. Now, force is equal to Kx from Hooke's law, F equals Kx. And so we can actually replace this F with Kx to give us Kx times X, or Kx squared. So these two expressions of the change in elastic potential energy, or the energy stored in the spring, are equivalent to each other. Right, let's just get rid of that to just clarify a little bit. So half Fx and half Kx squared are the same thing effectively because we've just substituted for F. All right, so those two are expressions for the energy stored within the spring at any extension X. And obviously, which one you use depends on which data you're given in the question. So let's have a look at a typical question. Here's one here. A spring is extended by 2 centimeters or 0.02 meters, so that's X, and the spring constant is 25. So that's K. So we've got K and X here. Calculate the potential energy in the spring. So the potential energy stored is equal to, in this case, we're going to use half. Now we've got K and X, so we're going to have half K X squared. All right, so the elastic potential energy is half Kx squared. Half is just a half multiplied by the K, which is 25, multiplied by X squared, which is 0.02 squared. And when you calculate all that, you get 0.005 joules of energy, or 5 millijoules. Okay, so that's a typical question. They tend to be quite simple questions on elastic potential energy. And that's it. All right, so we've got Hooke's law, we've got the definitions of elastic and plastic deformation, and we've got elastic potential energy and work done stretching a spring. Okay, that's it. Thanks for listening.